All right, today we're going to start a chapter that's about logic. There's going to be a good portion of this chapter where you might find yourself feeling like this isn't math. And it is math. There's just not going to be computations for a good portion of what we're doing. How many of you have taken critical thinking? Okay, so if you've taken critical thinking, some of this stuff is going to be old hat to you. You've done it before. So we'll see if that means that you like it any better now compared to someone who hasn't. I don't know. I usually get pretty good responses, so we're going to give it a go. So to start with, just a few basic terms so that we can make sure that we're on the same page as one another. Statement. A statement is a sentence that is either true or false. So, for example, I ate eggs for breakfast. That's a statement. And it happens to be true today. I did eat eggs for breakfast. Okay? A non-example, something that is not a statement, would be, what did I eat for breakfast? Instead of a statement, we would call that a question. The other kind of comment that can show up in here sometimes that's a non-example is something like this. Eat your breakfast. Do you know what we call that kind of a sentence? A command. Yeah, that's a command. So a statement that has a definite true or a definite false answer is a sentence that has that is a statement. All right, a negation. The negation is the logical opposite of a statement. It is written with a tilde. So if your statement is written as P, then your negation would be written as tilde P. Okay? So if the statement, I ate eggs for breakfast, is my statement P, then the negation of P would be what? What's the opposite of that? Yeah, exactly. I did not eat eggs for breakfast. Exactly. All right, so it sounds pretty straightforward, right? I did, I didn't. Or if somebody says, I didn't run today, then the opposite of that would be I did run today, right? And that's true. Those are very straightforward. But it gets a little trickier when certain language gets involved. That type of language is called quantifiers. There are two types of quantifiers. There are universal quantifiers. They refer to each and every element in a set. Words like all, every, no, or none. These are the statements that your parents get mad at you when you say it, something like, you always forget to lock your door, right? And you're like, no, yesterday I remembered, right? Yesterday I remembered. We had problems for a long time with our son locking his car doors, so we just told him he couldn't have a garage door opener because he can't trust that he will have his door of his car locked and not have access to our house, okay? Universal, always, never, those kinds of words. Existential quantifiers. Existential quantifiers refer to one or more elements in the set. So they use words like there exists, or at least one, or some. So if I talk about my locking the car door example, it would be sometimes I forget to lock my car door. Or you could say, at least once I forgot to lock my car door, okay? It's a much less volatile statement, right, than saying all and every and none. All right, the problem is that it's really tricky when we create negations with those words all and every and there exist kind of things. So I'm going to give you an example. We're going to talk about dogs going to heaven. It's a very old movie. I don't know if you ever saw that cartoon for kiddos. All dogs go to heaven. All right, so here's an example of of a statement that's a universal quantifier, right? It has the word all in it. Okay, every single dog, every single one. So what would it take? A negation means what is the least possible thing that it would take to make the statement false. That is way overkill. I don't need no dogs going to heaven. Yeah. Actually, even the least thing I could write is there's one. So some works. We could say some dogs don't go to heaven. Or you could say at least one dog doesn't go to heaven. Yes, ma'am.
If we say no dogs go to heaven, would that be wrong?
That would be wrong. Yeah. A negation is the least thing that it can change to make the statement false. Right? It's the conversation you had with your parents where they say, you always forget to do this. And you're like, yesterday I remembered. That makes their statement false, right? Their statement doesn't have to be false all the time. All it has to be false is one time to make it a false statement. Okay? All it takes is that one really awful dog. Just that one to make the statement false. Okay, so some of my classes this semester are hard. What would that take to make the statement false? What would be the negation? All of my classes are what?
Are easy.
That would be the idea. Are you guys with her? If some of my classes are hard, what would have to be true to get the opposite effect is that all of them would have to be not hard. We want to be careful because I bet you probably have some classes where you're like, it's not hard, it's not easy, it's sort of in between. Okay? So we want to be a little bit careful in our language. But there's actually two ways to write this one. So we could write all of my classes this semester are not hard. There is one other way we could write this. The one that you actually just gave. Is it Katie?
Yes,
Okay, I'm cheating, but I've got a list. The one that Katie gave is the most natural way to say what this negation is. But there is another technically correct way to say it, so I would like to show it to you. You could say, none of my classes this semester are hard. And for this one, that's a pretty good English kind of a descriptive statement too. Some of them feel a little bit more awkward when we switch the negations. Here's what I want you to notice. This is what type of quantifier? Universal. This is what kind of quantifier? Existential. This one is a existential, and these are universal. So write yourself a note down, big, bold, highlight, whatever it takes. Anytime you're doing negations with quantifiers, a universal negation becomes an existential, and when you negate an existential, it becomes universal, always. The opposite type of quantifier. So all becomes at least one. None becomes at least one. Some or at least one become either all or none. It just depends on how you phrase the rest of the sentence. Okay? Okay, so what we're moving into next are called truth tables. Okay? Truth tables allow us to show, hang on a sec. That didn't get cleaned off. Truth tables allow us to show all possible true and false patterns for statements. So we're going to first talk about negations and what that looks like inside of a truth table. So a truth table looks like a list. whatever your statement is called, we tend to use P's and Q's. I don't know really where that comes from specifically, but P's and Q's, and then R's if there's a third one. If your statement is true, then what can you tell me about the negation? It's false. That's exactly how we created the statements, right? And if your original statement is false, then the negation is true. So this is the most simple truth table that we will see. Everything else will have more T's and F's in it than this. And they will, because we're going to deal with compound statements. So compound statements are statements that join statements with connectives. The three connectives actually that we're going to focus on are and, or, and if then. What you saw me erase at the very beginning is the fact that this word and the word but mean the same thing in a compound statement. So let me just give you a verbal example. If I say, I am a math professor and I am a mom, it's the same statement as saying, I'm a math professor, but I'm a mom. It just means both of those things are happening, right? It's actually the word and. There's some sort of context that you might read into it, sort of like, what does she mean by that differently, right? But in terms of the truth statements, they're actually equivalent. So the first one we're going to talk about is we're going to talk about the and statement. The and statement is called a conjunction. And a conjunction is true if both statements are true. So if we have a statement P and we have a statement Q and it's an and statement, it looks like an upside down V. Or if you want to, you can think it looks like a pointy N, like in the middle of the word and. I mean, like a really pointy N, right? Yeah, really. And what we're going to do next is we're going to create the truth table that goes along with this statement. So you're going to create a 3-column truth table. One column is statement P, one column is statement Q, and one column is statement P and Q. And what we want is we want to represent all possible true and false combinations of the two statements. For example, if statement P is true, statement Q could be true as well. We could just have 2 true statements. But we could have statement P true and statement Q could be false. Right? But likewise, we could have statement P false and statement Q true. What's my last possibility? Both false. And every truth table starts out like this. True, true, false, false, true, false, true, false. So no matter what you have to do next, you can always start a truth table because the first 2 columns are always the same. Okay? Always, always. So we're going to talk about and statements, and we're going to talk about it hopefully using people you know. That's the way I always try to do this. So the first column is going to be me. You know a little bit about me because I've shared a little bit about myself with you. And if I walk into the classroom and I say, I teach math and I'm a mom, you would say, that's true. And the reason that you would say that that's true is because both of the statements individually are true. Right? Cool. All right. So let's say then, you guys may not know, well, let's take somebody that you do know. How about Dr. James? No, that one won't work. I need to use Dr. Auk. Do you guys know Dr. Auk? Have some of you had him in class? How about Dr. Tucker? Okay, I've got some nods. Okay, so Dr. Tucker is the chair of the math department, and she is not married, has no children. That's their context, okay? So if she walks in here and she says, I teach math, and I'm a mom, you would say that's false because she isn't a mother. All it takes is for part of the statement to be false and an and statement's false. All right, how about Miss Dr. Young? She's doctor now, yes. Dr. Young walks in, and Dr. Young says, I teach math and I'm a mom. This is not true. She does not teach math. She is mom, so it's like half true, right? But all it takes is for a portion of the statement to be false and the whole thing is false. We'll use Dr. James as my last example then. Do you guys know Dr. James? Excellent. Dr. James walks in and Dr. James says, I teach math and I'm a mom. And after you laugh, you would say, no. In fact, that's as false as it could get, right? Because neither individual statement is true. And that's the way that a conjunction, an and statement, works. You good with that? Okay. The second one is called a disjunction. A disjunction is an or statement. And an or statement is true if either of the individual statements are true. It may sound weird, but it's technically true. So again, same kind of a truth table. We've got column P, column Q. And what I told you a minute ago is that the first two columns are always the same. So column P goes true, true, false, false. And column Q goes true, false, true, false. And again, the reason why is because that captures all the possibilities. Now, an or statement is written actually as a V between them. So it looks like PVQ. Okay? So the third column is PVQ. It's P or Q. So we're going to use the same people that we just talked about, and they're going to walk in and they're going to say the same things to you, except they're going to use the word or in the middle. So I'm going to walk in and I'm going to say I teach math or I'm a mom. And you're going to look at me and say, well, that was a weird way to say this, but yeah, that's true, right? Or means either or both. It doesn't mean either or and it can't be both. So this is a true statement with an or between it. Awkward and weird, but it's true. So the next one I had was Dr. Tucker. Dr. Tucker walks in and she says, I teach math or I'm a mom. And I told you she's the math department chair, so that would be true. She does teach math. So that's a true statement. Dr. Young walks in and she says, I teach math or I'm a mom. And you say, that's a true statement. She is in fact a mom. Doesn't teach math, but she's a mom. But then if Dr. James walks in and he says, I teach math or I'm a mom, again, you kind of chuckle underneath your breath and you say, I don't think so. That would be false. Okay? So in order for a true statement to be, for a disjunction to be true, either individual piece or both is true. It's easier to say the only way it can be false is for both statements to be false. All right, so what we're going to do next is we're going to take a look at creating a truth table for just a general statement. So on this one, there's actually a statement given to you. It has several pieces to it, and each piece has to have its own column in the truth table. So when we create a truth table for a generalized statement like this, we have to start with columns P and Q. And it doesn't matter that there's no Q all by itself in the problem. There's a Q in there, so there will be a column for Q. Your next column takes a look at what else you might need in order to put it all together. Well, hopefully you noticed that there's a tilde in our problem, right? So you're going to need a column representing that quantity. So you're going to need a tilde Q, or a negation of Q column. Then you're going to put it all together with the connective that's between there, which is the and connective. So your last column is P and tilde Q. There's still only two statements. It's a P statement and a Q statement. So there's still the same arrangement at the beginning. True, true, false, false. True, false, true, false. All that's the same. Now, we did a negation, but we did it in a much simpler context, but it works the same way. When we're looking at a negation statement, we look back at the statement it's negating. So we're looking back at this column. If the statement is true, what's the negation? False. And if the statement is false, what's the negation? True. So we simply reverse the entire previous column. So it's false, true, false, true. Our last column then combines statement P and statement tilde Q. And it combines them with the connective that's in and. So when is an and statement true? When there's two truths. But I don't need the Q column to do that, right? I'm ignoring my Q column as I'm making this choice. So the first row has a true, false on it, right? So a true statement and a false statement connected with the word and is false. Your second row has a true and a true on it, which makes it true. Your third row has a false and a false on it, which makes it false. And your fourth row has a false and a true on it, which makes it false. And then your truth table is complete. I'm trying to see where I want us to be. Okay, let me do just a couple more things and we'll stop for today. Logically equivalent. Two statements are logically equivalent if they have the same truth value in every possible situation. And it's written as a triple inequality. That's what logically equivalent looks like. Two statements that mean the same thing. We saw an example of that early on. I know promise we'll be back to the screen. But right here, these two statements that we wrote that were the negations, there were two negations. They mean the same thing. All of my classes this semester are not hard means the exact same thing as saying none of my classes this semester are hard. Those are logically equivalent statements. They mean the same thing. So when does that happen? When you have ands and ors. Well, that's what De Morgan's laws tell us. De Morgan's laws tell us that if you have an and statement and you take the negation, what you see is that each of the individual statements are negated, right? Tilde P, tilde Q. But you also should notice that the and becomes an or. Okay? So it's almost like there are three items inside here and they all change. Ands become ors. Tildes affect statements. If there were a tilde on the statement, we would remove it. All that good stuff. And the same thing happens to or statements when I negate them. It's almost like I'm distributing the tilde through, and it affects every piece. So I have a tilde P when I'm done, I have a tilde Q when I'm done, and I have an and statement when I'm done. So we are going to use that logic to do example 3, and then we'll pick up with example 4 next time because we won't have time to finish example 4 if I start it. So if I use De Morgan's laws to find the negation, I'm asking you to find the negation of P and tilde Q. This is just a symbols argument right now. So if I'd moved the tilde through, what will this look like? What will the first piece become? Tilde P. And then what will I write down? An or statement. And then I will have Q when I'm done. Right? It's like the opposite of -2, right? Like negative 2 becomes positive 2. It's like that. The opposite of a tilde is not having a tilde. Okay? So what we're going to do next time, I'm going to show you what we're going to do. We're just not going to do it. We're going to do 2 truth tables. One truth table is going to be the left-hand side of this inequality. Okay, with all the pieces, just like I did that other truth table. And the second truth table is going to be the right-hand side of this equality. And what we're going to see happen to logically equivalent statements is that the final column of both truth tables has the same T's and F's and in the same location, in the same place. And that's what actually proves that the 2 statements are logically equivalent.